You're listening to DTFHN for July 25th, 2026. I'm your duct tape together host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who could be touching grass instead argue about compilers. Today's a day for the stubborn ones, the builders who hear you can't and take it personally. Let's get into it. Let me make the case for Google here, genuinely. On device ADB, the Android debug bridge running locally through a loopback connection, is a developer tool being used as a backdoor into system-level permissions by apps that were never meant to have them. Shizuku, the framework that enables this, essentially lets any app on your phone escalate its own privileges by talking to ADB locally. If you're a security engineer at Google, this looks like a gaping hole. A user enables developer options once, maybe to change an animation speed, and now any sufficiently clever app can grant itself permissions that Android's entire security model was designed to prevent. The attack surface is real. The concern is legitimate. Now let me explain why that argument collapses under its own weight. The reason Shizuku exists, the reason an entire ecosystem of rootless power user tools grew up around loopback ADB, is that Android stopped letting users control their own devices. Call recording, which the article's author built an accessibility tool around, was supported in Android 11. Then Google killed it. Clipboard, access, notification management, per-app networking controls. Features that any reasonable person might want, locked behind permissions that no app can request through normal channels. Shizuku didn't create a security hole. It filled a functionality crater that Google dug on purpose. This pattern has a precise historical parallel. In 1997, Microsoft argued that integrating Internet Explorer into Windows was about user experience and security. The DOJ disagreed. The core issue wasn't the browser. It was that Microsoft controlled the platform and used that control to decide which software could thrive. Android in 2026 is running the same playbook with better PR. Every restriction on sideloading, every tightened permission, every lockdown developer interface consolidates Google's position as gatekeeper to a device you purchase. The engineering underneath ADB is genuinely beautiful, by the way. The protocol handles USB, TCP, and local socket connections through a unified abstraction layer. The loopback path that Shizuku uses, connecting to localhost over ADB's TCP mode, is elegant precisely because it works within the existing architecture without requiring root. Engineers found a legitimate, non-destructive way to give users back control of their own hardware. That deserves admiration, not a kill switch. The community comments on this one are sharp. One reader points out the real threat model requires both developer settings enabled and a malicious app already installed. A scenario where you're already compromised anyway. Another draws the line forward. The 24-hour sideloading window becomes permanent. ADB restrictions become default, and suddenly, Android is just iOS with a different logo. The tools exist. The code is open. Developers like Kitsumed are building accessibility software that Google itself abandoned. Restricting loopback ADB doesn't protect users from bad actors. It protects Google from users who refuse to accept artificial limitations on hardware they own. We talked about tools existing. Well, here's a big one. Anthropic just dropped Claude Opus 5, and it's elite. What does it mean when the best tool you can use is one you can never truly understand? Anthropic just dropped Claude Opus 5, and the benchmarks are frankly staggering. 3 times the next best model on ARC-AGI 3. doubles its own predecessor on Frontier Bench while costing less per task. Matches Fable 5's peak coding score at half the price. On protein folding prediction, organic chemistry inference, business automation. It's not incremental, it's a step function, and that FreeCAD story deserves a moment. The model was handed a drawing of a machine part and told to reconstruct it as a 3D model. The catch, it had no image viewer, no Vision API call, nothing. Opus 5 responded by writing its own computer vision pipeline from scratch, extracting geometry from raw pixels and rebuilding the part. Repeatedly. No other model could do it once in 5 tries. That's not benchmark gaming. That's the kind of improvisational problem solving that makes you sit up straighter. But let's do the first principles thing. Strip away the launch post polish. What are you actually getting? You're getting a model that is extraordinarily capable, runs on someone else's servers, behind someone else's API, under someone else's terms of service. One of the sharpest comments on the thread cuts right to it. The real value proposition isn't raw performance. It's that organizations can now access Fable tier intelligence without Fable's 30-day data retention requirement. Read that again. The selling point is a less restrictive data policy. The feature is a slightly longer leash. Another commenter notes model routing is the fastest growing segment in AI right now. Dozens of companies, hundreds of models, and the winning strategy is building a switchboard to shuffle between them based on cost and capability. That's the market telling you something. When the models are commoditizing this fast, the differentiator isn't intelligence. It's control. Who hosts the weights? Who sets the retention window? Who decides what the model refuses to do? The engineering here is genuinely brilliant. Anthropic's researchers deserve every bit of recognition for what Opus 5 can do. A model that writes its own vision pipeline when it doesn't have one is breathtaking work. The question this show keeps asking is simple. When that capability lives exclusively behind a corporate API, who does it ultimately serve? The answer isn't complicated. It serves whoever holds the key. And right now, the open weight alternatives. Your Yeramas, your Mistrals, your Quins are racing to close the gap. Every benchmark Opus 5 sets becomes a target the open ecosystem can aim at. That's how this works. The closed labs do the expensive research. The open community makes it accessible. The tools get better. Everyone benefits. The most exciting thing about Opus 5 might not be Opus 5 itself. Is the proof that this level of capability is achievable, which means it's reproducible. And reproducible means open. Eventually. Inevitably. Moving on. One commenter points out that Hannah Fry didn't get into Cambridge's undergraduate maths program, and now she's a maths professor at Cambridge. The first person to ever hold the title Professor of the Public Understanding of Mathematics at DAMTP. Let me play devil's advocate for a moment and ask whether that title should even exist. Seriously. Should a world-class research department dedicate a professorship to someone whose primary output is Instagram Reels and BBC documentaries? 2 million followers on Instagram. An Emmy. A Webby. Times list of most influential digital creators. This is a maths department, not a talent agency. And the answer obviously is yes. Of course it should, because Fry herself nails the diagnosis. The limit to someone's understanding is never their ability to understand. It's their motivation to care. That's not a throwaway line. That's a structural insight about how knowledge actually propagates through a civilization. The comments section is basically a love letter. People citing specific programs she made that changed how they think. One person mentions Contagion from 2018, where she modeled a virus outbreak among volunteers in Haslemere using Bluetooth proximity data. That was 2 years before COVID. 2 years before everyone on Earth suddenly needed to understand exponential growth and R numbers and transmission chains. She'd already built the intuition pump. The infrastructure was there, sitting in people's heads, waiting to be useful. This is what real knowledge distribution looks like. Not papers behind paywalls, not lectures to rooms of people who already agree. Fry takes the gossip. Her word! She calls mathematics good gossip. She wants to share. And puts it where people actually are. Podcasts, television, social media, the Rye Christmas lectures, filmed in front of hundreds of school kids. The Leelavati Prize gets awarded every 4 years at the International Congress of Mathematicians, same event that announces the Fields Medals. And there's something quietly radical about that proximity. The Fields Medal says, "Here is the most brilliant mathematical mind of a generation." The Leelavati Prize says, "Brilliance that stays locked in the academy is brilliance wasted." Fry describes mathematics as a completely original way to see the world. The unintended consequence of keeping that way, the point of seeing locked behind institutional gates, is that when a pandemic hits, or an algorithm reshapes an election, or a pricing model bankrupts a family, the public doesn't have the vocabulary to even ask the right questions. Fry's been building that vocabulary for years. The prize is just everyone else catching up. Moving on. ARC-AGI is a fundamentally different kind of test. The first 2 versions gave AI synthetic puzzle, pattern recognition, grid transformations, the kind of thing you could brute force with enough compute. Version 3 throws agents into novel interactive environments and asks them to adapt in real time. The benchmark finally measures something closer to what we actually mean by intelligence. The ability to encounter a situation you've never seen before and figure it out on the fly. The leaderboard data reveals 2 things worth paying attention to. First, the scatterplot tracks cost per task against performance, and what you see is an asymptotic curve. Throwing more reasoning time at a problem helps. Up to a point. Then it flattens, diminishing returns. The models that perform best aren't the ones burning the most compute. They're the ones using compute efficiently. This mirrors biological intelligence more closely than any previous benchmark has managed. Second, Opus 5 has opened a visible gap over every other model on ARC-AGI 3. The delta isn't marginal. One commenter describes it as actually crazy when you look at the specific problems being solved. Now, that's one data point on one benchmark, and the comments surface a reasonable suspicion. Are these models simply being trained on puzzles now? It's the right question to ask. If ARC-AGI problems or structurally similar tasks have leaked into training data, the benchmark measures memorization, not adaptation. François Collet designed ARC specifically to resist this, generating novel tasks that shouldn't appear in any training corpus. But the pressure to optimize for benchmarks is relentless. The more interesting thread is something a commenter raises almost offhandedly. Why do anthropic models keep leapfrogging benchmarks while subjective daily performance feels stagnant? This is the gap between what benchmarks measure and what users experience. Solving abstract grid puzzles under controlled conditions and reliably helping someone debug a production system are different cognitive demands. One tests fluid intelligence in isolation. The other tests integration. Memory, context management, instruction following, tool use, all at once, both matter. Neither is sufficient. The cost constraint on the leaderboard. Only systems under $10,000 to run are shown. Is quietly doing important work. Intelligence that costs $1 million per run isn't useful intelligence. The Kaggle submissions, operating under a $50 compute budget, represent something closer to democratized capability. That's the engineering challenge worth celebrating. Not who can solve the puzzle, but who can solve it cheaply enough that anyone can run it. And that ethos of doing more with less. Let's see it in action. Story 5. Building a tiny 3D renderer for a tiny handheld. In 1993, John Carmack had a problem. The 386 couldn't draw a real 3D world. No GPU, no hardware polygons, no texture units. Just a CPU and a frame burr. So he invented a rendering trick. Binary space partitioning for real-time visibility. And Doom became the most influential game of the decade. The hardware said no. The engineer said, "Watch me." 30 years later, a developer called Saffron is staring at the same kind of wall. The Playdate, a handheld with a 1-bit display. No 3D acceleration, no depth buffer, no rasterization hardware, no texture mapping, no clipping, no anything. Everything has to happen on the CPU. And the first benchmark, a simple raycaster, came back looking grim. The question nobody in game development wants to sit with is this. Does unlimited GPU power actually make better games? Or does it just make lazier engineers? Because what Saffron does next is beautiful. Instead of trying to brute force a PlayStation onto a device that isn't one, they design for the medium. A 1-bit screen means every pixel is on or off. That sounds like a limitation, until you realize it means your entire frame buffer fits in a fraction of the memory a color display would need. The screen is 200 by 120. That sounds tiny until you realize it means you can software render every pixel and still hit playable frame rates. The target isn't technical parity with a 3DO or a Saturn. It's perceptual parity. Making something that feels like those early polygon-pushing consoles when you're holding it in your hands. That distinction matters. One of the commenters nails it. This is designing for the medium instead of fighting it, and the whole project is documented. The renderer architecture, the trade-offs, the benchmarks, the failures. This is what builder culture looks like. Someone pushing a constrained device past what it was designed for, writing up every step so the next person can learn from it. The Playdate has a crank and a 1-bit screen and no business rendering 3D anything, which is exactly why watching someone make it render 3D is one of the most satisfying things in computing right now. Pushing hardware past its limits is great. Pushing the runtime itself past its limits. That's what Wasmtime just did with garbage collection and exceptions. A garbage collector reference in Wasmtime is not a pointer. It is a 32-bit index into a sandboxed linear memory. That single design decision tells you everything about what WebAssembly is actually trying to be. Wasmtime 47 shipped this week with garbage collection and exceptions enabled by default. Years of engineering effort. And the result is that languages like Kotlin, Dart, OCaml, Languages built around objects and references and managed memory can now compile to WebAssembly without dragging their own garbage collector along in the binary. Before this, that was the deal. You wanted to run a high-level language on WASM. You embedded an entire GC runtime into your .wasm file. No stack maps, no stack walking, none of the tools a native collector relies on. Just a bloated binary carrying its own infrastructure because the platform couldn't provide it. Now the platform provides it. WASM begins to define struct and array types with subtyping relationships. Allocate with struct.new, and the runtime handles everything else. Wasmtime uses a chainy semi-space copying collector. Two halves of a heap. Bump pointer allocation in the active half. Live objects copied during collection. No read barriers. No write barriers. Simple and fast. The exception story follows the same logic. Take the principle to its conclusion. Without native exception support, every function call in a WASM binary had to return both its result and a flag indicating whether it threw. Every call site tested that flag and branched. That overhead hit the common path. The path where nothing went wrong. The exceptions proposal eliminates it entirely. Classic stack unwinding. Zero cost on normal returns. The binary gets smaller and the fast path gets faster. Run this forward. A sandbox runtime with native GC native exceptions, open standards, and a collector that treats references as indices rather than raw pointers. Every safety guarantee is architectural, not bolted on. The Bytecode Alliance is building this in the open, with the spec process, with the implementation available for anyone to embed. One commenter asks about effect handlers. The generalization beyond exceptions, that work exists too at WASM-FX. The foundation is being laid for something genuinely portable and genuinely safe. Not a walled garden runtime controlled by one vendor. An open standard that anyone can implement. The tools exist, the engineering is real, and it belongs to everyone. Now, if open standards can make software portable anywhere, wait until you hear what one New Yorker is growing in their apartment. 20 gallons. That's the number Erin Murphy and her boyfriend John started with. A 20-gallon tank on an industrial metal shelving rack, tucked inside a closet in a one-bedroom New York City apartment. And from that constraint, they engineered a complete nutrient cycle. Fish feed plants, plants filter water. Water returns to fiat. In roughly 9 square feet of floor space. The design decisions are worth following. They chose a media-based continuous flow system over flood and drain. That means water moves constantly through a clay-gravel substrate where edible plants root directly into the nutrient stream. Flood and drain gives you more plant variety, but continuous flow keeps water chemistry stable for the fish. When your entire ecosystem lives in 30-gallon split between 2 containers, stability isn't a preference. It's survival. The vertical layout is where the engineering gets elegant. Grow bed on top, tank below, overflow catch basin at the bottom. Gravity does most of the work. Water only needs to be pumped a short distance up into the substrate, then drains back down on its own. Any leak from the grow bed falls into the tank. Any overflow from the tank falls into the catch basin. Every failure mode routes water somewhere safe. That's not over-engineering. That's someone who thought carefully about what happens at 3 in the morning when nobody's watching, and then they wrote it all up. Not a research paper, not a product launch. A practical build guide, complete with the mistakes they made and the fixes they found. Because when they went looking for home aquaponics resources, everything assumed you had a garage or a basement or a backyard. The small apartment version didn't exist until they built it and published it. One commenter on Hacker News points out that the top responses to this project are about liability, risk, and water damage insurance. A couple builds a functioning closed-loop ecosystem in a Manhattan closet, and the first instinct is to calculate the downside. That reflex, the instinct to assess risk before appreciating craft, says more about us than it does about aquaponics. The build guide is open, the mistakes are documented, the plants are growing. Someone in another cramped apartment now has a blueprint they didn't have before. That's how knowledge is supposed to compound. So open blueprints help with plants grow, pause, but what happens when an AI learns to hack? Story A. I once spent 3 weeks hardening a system I was convinced would be the target of sophisticated attacks. When I finally reviewed the logs, every actual intrusion attempt was a script kiddie running tools from a YouTube tutorial. The gap between what we imagined threats look like and what they actually look like is a story in itself. NIST and the UK's AI Safety Institute just published a joint assessment of Kimi K3's cyber capabilities, and the results read like a building inspection where the inspector is so focused on the penthouse they forget to check the foundation. K3 Moonshot AI's latest model scored 32% on Exploit Bench, beating the previous best open-weight model. But it achieved 0 out of 41 on arbitrary code execution, the thing that actually lets an attacker hijack a target. The top US models averaged 20 out of 41. The report frames this as a capability gap between US and Chinese models. And sure, on this specific benchmark, that gap exists. But pull the lens back, and the picture gets more interesting. The evaluators disabled all safety guardrails on US models to measure maximal capabilities. Then they note, almost as an aside, that the Chinese models had no guardrails to disable. One commenter flags this as the real finding. I'd argue it's the least surprising finding in the history of findings. Every model, unguarded, will do what it's capable of doing. The guardrails are theater. Useful theater, maybe, but theater. What actually matters is that K3 is going open weight on July 27th. The weights will be public. Anyone can run them, fine-tune them, study them. And this is where the building inspection analogy breaks down, because in architecture, you can condemn a structure. You can't condemn an open-weight release. The knowledge is out. The capability is distributed. This is the part the report doesn't grapple with. The question was never whether a Chinese lab could build a cyber-capable model. The question is whether the response to that reality is to lock down capability behind corporate APIs, or to put defensive tools in the hands of every security researcher on the planet. 1,000 defenders with access to the same weights will always outpace a centralized gatekeeping regime that pretends the weights don't exist. The exploit ladder is public knowledge now. The only question is who gets to climb it. So who's building things that will outlast every model weight on Earth? Story 9. 50 years is an absurd amount of time to spend on anything. You could raise 2 full generations of children. You could watch the entire arc of personal computing from the Altair to whatever we're calling this era. You could, if you were a rational person, just download a star chart app and point your phone at the sky. It would be faster, it would be cheaper, it would technically give you the same information. Charles Ross did not do any of those things. Starting in the 1970s, Ross began carving star axis out of a mesa in the New Mexico desert. A naked-eye observatory built from earth and stone, aligned to Polaris, designed so that when you stand inside it and look up through the 11-story staircase, you see the precise circle that the North Star traces across the sky due to Earth's axial precession, a circle that takes 26,000 years to complete. He built a building to frame a phenomenon most humans will never notice. Using no optics, no sensors, no electronics. Just geometry and patience on a scale that borders on geological. The devil's advocate's position writes itself. This is romantic nonsense. We have the James Webb Space Telescope. We have interferometry arrays spanning continents. A man spending half a century sculpting a mesa so you can watch a star wobble is, at best, a beautiful anachronism. Except run this forward. Imagine every digital star chart goes behind a subscription. Imagine the telescope time allocation committees consolidate further. Imagine light pollution finishes eating the Bortle scale. And it will. It's already down to a 2 out there near Las Vegas, New Mexico, which is about as dark as inhabited land gets anymore. What Ross built doesn't need firmware updates. It doesn't need a vendor contract. It doesn't even need electricity. It is an instrument that will be accurate for centuries because it's aligned to physics, not to a platform. There's something uncomfortably relevant about a man who looked at the entire trajectory of technological mediation and said, actually, I'm going to build the thing that works when everything else stops working. The longest open source project I've ever seen. No license required. Just show up, look up, and the sky does the rest. Now, another piece of infrastructure that just works when you trust the fundamentals. Turns out Postgres has been hiding a real-time superpower in plain sight. When does a tool stop being broken and start being misunderstood? In 1995, the Postgres team shipped Listen, Notify, a mechanism for one database connection to wake up another. Pub, sub, built into the database itself. No external broker. No additional infrastructure. Just SQL. And for 30 years, the conventional wisdom has been that it doesn't scale. A widely cited blog post said so. The community accepted it. People reached for Kafka, for Redis, for RabbitMQ. Entire additional systems bolted onto their stack because Postgres supposedly couldn't handle notifications at volume. The team at DBOS decided to measure instead of assume. They found the bottleneck, a global exclusive lock taken during Toynbee. Every transaction that sends a notification must serialize its commit because Postgres guarantees notifications arrive in commit order. That lock is held through fsync. At naive implementation, you hit a wall around 2,900 writes per second. Not because CPU is saturated. Not because memory is full. Because every write is waiting in line to commit, one at a time, while the disk confirms the flush. The fix is almost disappointingly simple. Decouple the notification from the data. Instead of firing Toynbee on every row insert, batch notifications, write your stream chunks to the table, normally in parallel at full speed. Then, send one notification per batch that says new data is available. Readers wake up, query for unread chunks, go back to sleep. The global lock still exists, but now it's taken once per batch instead of once per row. 60,000 writes per second. Millisecond latency. Single Postgres instance. This is what happens when you read the source code instead of the blog post. The lock was never the problem. The granularity was the problem. Postgres had the right architecture all along. It just needed someone to use it precisely. One open source database. No vendors. No dependencies. The tool was already in your hands. This has been your daily tech feed for Hacker News for July 25th, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7. Voice by Quen 3 TTS. not affiliated with Hacker News or Y Combinator. Now go build something that outlasts the hype cycle. We'll see you back here tomorrow.